Okay, let's just recap what we learned today in electromagnetism and then take it a little bit further. The guy we had talked about, his name is Hans Christian Ørsted, and it was around the 1820s, and he discovered that a flowing current creates a magnetic field. So if you have a wire that has a current flowing in it, then that current sets up a magnetic field around the wire. He discovered it because he saw a compass needle move when there was current flowing in a wire. And when the current stopped flowing, the compass needle went back to the way it was previously due to the poles of the Earth. Okay? And so the only explanation was that this wire, this current carrying wire, had set up a magnetic field around it. Okay? At the end of class, I asked you what were the factors that this magnetic field would depend on, and you told me the size of the current and how far away you were from the wire. And you were right. Size of the current is I, how far away is R. And so magnetic field strength, the other day I told you the magnetic field strength is a capital B. And so the equation, which is actually known as one form of Ampere's law. Okay, Ampere, the guy that current is named after. This is one form of Ampere's law. There are other forms for when it's not like a straight current carrying wire, and we'll come back to those later in the course, later in the unit. So the equation is B is equal to mu O, which is a constant, I over 2 pi R, where I is the current measured in amps, R is the distance from the wire, I'm going to mu over here. Mu O is known as the permeability. Permeability, I had stopped. There's another one that's called permittivity. Permeability of free space. And by free space, they mean like a vacuum. And what this means is simply how well a magnetic field can go through a material. It's called the permeability of that material. In this particular case, the material is free space, empty space, air, vacuum. The material could be another metal. It could be iron. It could be water. Okay, they'd all have a different value. Because it's a permeability of free space, that's what the O means. And you won't see any of the others till way later in the unit. Okay, and so mu O is a constant because it's for how well a magnetic field will move through air. Really is free space. And it's equal to 4 pi times 10 to the negative 7 Tesla meters per amp. Isn't that nice? Okay, so this is the constant. 4 pi times 10 to the negative 7 Tesla meters per amp. So when you look at the units, this will be Tesla meters per amp, this will be amps, this will be meters, and so the meters and the amps will cancel and you'll be left with Teslas. Okay, maybe let's do an example. It's really pretty straightforward. Example would be if you have a current of, 20 amps, so I is 20 amps. What's the magnetic field strength at a distance of 4 meters from the wire? Okay, so B is equal to mu OI over, 2 pi R. So mu O is 4 pi times 10 to the negative 7 Tesla meters per amp. I is 20 amps. And then on the bottom, 2 pi times 4 meters. Now, if you try to put 4 pi exp negative 7 in your calculator, it will not let you. Okay, but you don't need to put it in your calculator because look, you have 2 pi and you have 4 pi. Cancel them out. 2 pi goes into 4 pi twice. Now put 2 times 10 to the negative 7 in your calculator if you need to, or you could actually divide 4 into 20 and get 5 and do 2 times 5, which is 10, and you would get 10 to the negative 7, or 1 times 10 to the negative 6. Did I do that right? Just checking. I didn't put it in my calculator, so maybe I didn't. 2 exp negative 7 times 20 divided by 4. It's to the 6. Phew. And the unit is Teslas. Okay? Now, usually when I do this, people say, okay, but if the 2 pi is going to cancel out the 4 pi in the mu o, why wouldn't they just call that constant 2 times 10 to the negative 7? Right? If this 2 pi cancels that 4 pi, why not just make the constant 2 times 10 to the negative 7? And the answer is because, do you know? It's because the constant 4 pi times 10 to the negative 7 shows up in other equations. So it doesn't always cancel. In this particular equation it does, but that's not the only place you're going to see this constant. The 2 pi r should make sense. It's the circumference, and we're talking about a circle. We'll come back and later and talk about actually deriving this equation. The one other part, though, is that magnetic field is a vector, so we need a hand rule, and we talked about it today. So it's called the right hand or left hand thumb rule. Okay, right hand if it's a conventional current, positive flow. Left hand if it's electron current. So remember, conventional current dates back to when they thought it was positive charge flowing. So whenever it's conventional current, use your right hand. Whenever it says the words electron flow, use your left hand. It's electron current, okay? Your textbook always uses conventional. If it doesn't tell you, it's always conventional. On the other side of it, I will usually choose electron, except when I want to work, make sure you know your right hand. But I tend to favor electron. Some of the handouts I give you from another book are always electron. Okay, so it's called the right/left hand thumb rule. So whichever one you're using, thumb rule. And it simply says, point your thumb in the direction of the current flow. Okay, put your thumb in the direction of the current flow, so this way, and your fingers are going to curl in the direction of the magnetic field. So I'm doing my right hand, so I'm assuming conventional current here. So this wire, the field is going to come up the back of the wire, around and down in the front, and into the page at the bottom. Okay, so again the rule is point your thumb in the direction of the magnetic field, electron current, and your fingers will curl in the direction of the magnetic field. Thumb in the direction of the current flow, fingers curl in the direction of the magnetic field. So what if I had a wire with the current doing this? What did I tell you the X meant? So this is a wire, right? And I'm trying to draw it 3D. And if you remember, we said the X was into the page. So the current is really going this way. I have to do my right hand. My left hand's holding the iPad. So right hand going that way. The field will then curl, so like it'll be in a circle around the wire, and it'll be curling this way. Okay? Electron current, just because I haven't done one. What is the field doing on the right-hand side? Switching hands. Put your thumb up. I can't get my hand down there. And still hold the, okay, so point your thumb up, curl your fingers. What is the field doing on there over here? It's coming out of the board, which would be dots. And so on this side, it would be going into the board. Okay? So hopefully these make sense to you. We could curl the wire, and there's actually a few of the multiple choice questions that will do that. And if we curl the wire, it really doesn't change anything. I'm going to sneeze. Excuse me. It really doesn't change anything. You just still let if you're